Okay, this is the last things about light and lenses that we're going to cover in terms of the lenses and how we make them and what we deal with, how we deal with them. One thing you might have noticed in the lens ray diagrams and in the calculations with converging lenses and things like that, things end up upside down a lot. We end up with images that are maybe shrinking in some cases. Lots of things that we may or may not like. So it turns out there's a lot of times when we actually want to use a combination of lenses. Very often we use one lens to maybe position the focal point for the second lens just right. In fact, if you've ever used microscopes, things like that, oftentimes we use two lenses to make sure we're looking at something upright. It'd be really hard to adjust, say, a slide on a microscope if everything is upside down and reversed. So you're going to you want that simplicity and that to be there. So real quick, a couple of things we want to point out. Okay, when we're dealing with multiple lenses, okay, what's really important is that we understand that if we go through and we create our first image right here, right? So here's our image from the first object. It goes through the light, through the first lens. Great. Well, the distance of the image, okay, is the distance from the first lens to our image. But the distance from that image to the next lens is going to be considered the object distance for object 2. We're going to use the actual image from the first lens to give us the position of the object for the second lens. And so this is a pretty basic idea where we do end up with a couple of concerns, okay, a couple of things to think about. So let's say that this object distance, they give us an example in here, but let's say that it's 20 centimeters to where they wound up being. Well, if it's 80 centimeters distance, then the DO for part 2 would be 60 centimeters, okay? And that's going to be useful in calculating the final image, or DI2, the image distance for the second part, for the second lens. One thing that you do have to be very careful about, and I really want to make sure this is clear, sometimes when we put these lenses together, we end up doing it in a way where maybe the light, I'm going to exaggerate this a lot, maybe the light doesn't gather until after we've passed the second lens. What that means for us is that this distance here, DO2, will be negative, okay? Because it's on the back side of the second lens, its image, or its object length, will be negative. Now, whether or not the image ends up being negative, that's a different question altogether, okay? So that's something that we really have to think about, okay? Is because we're on the back side, this is coming out negative, okay? And so it's really important that you take time to process where are you relative to the second lens, because you're going to need that information from your first object, all right? So that's just something to think about. Otherwise, the same formula works, you know, our 1 over DO plus 1 over DI equals 1 over F. You're still going to use the same formula for your lens calculation to figure out how far out the image would be. Essentially, where do you want to put your eye so that it's focused, so that you get a clear image? And that's what that's all about. So 2 lenses, just remember the image from the first lens becomes the object for the second lens. And then it should be pretty straightforward for you to calculate from there. I mean, there's challenges and things along those lines. But the second piece that we really want to talk about, and for anybody who has any interest in becoming an eye doctor, whether it's an optometrist, ophthalmologist, just imagine I said the word correctly. Anyway, if you're interested in the eye and things like, or maybe you just want to know about your own eyes, how is it my lenses are shaped? Because we don't have, in our eyeball, we don't have a lens that is shaped like a traditional converging lens. We have one of these types where it's convex on the outside and concave on the inside. Well, that's going to change our focal length significantly. And this is the same thing with glasses. when you get glasses, they're not flat on the back, although there are some that are flat on one side, but typically they're not the same curvature on both sides, and it's certainly not that traditional double convex. That's not what we're used to seeing. We're used to seeing something more like this meniscus. So when we see this, we have to have a new way of calculating. And what we have is called the lensmaker's equation. And this is a great equation. It's going to allow us to solve all of these. All right, so first, 1 over f. That's going to be our focal length. N is our index of refraction, which we have from previous. It'll be like 1.5, 1.52, somewhere in that ballpark. Remember, water is 1.33. Air, we're going to call it 1. Then we have R1 and R2. Well, R1 and R2 are the two different radiuses of curvature. Here's the deal. At the end of the day, it doesn't matter which one's R1 and which one's R2. You could say R1 is the one that's first going to have light, and R2 is the second one that's going to have light. It doesn't really matter as long as we just use both of them because it's an addition problem. However, we do need to be able to distinguish between positive and negative radiuses of curvature. Okay, if the surface is convex, meaning it sticks out, okay, R will be positive. If it's concave, meaning that there's a cupping shape on that side, there's a hole or concavity, then we're going to be considering that surface to be negative. So R here would be negative. And so convex is positive, concave is negative, and that's going to allow us to calculate. Pretty simple stuff. Just make sure that you're going through the process of algebra and solving really slowly and cautiously. Make sure you move things the correct way. But otherwise, you should be good to go. Good luck, and we'll see you in class.